Hello and welcome to this video about data structures. In this video, we'll investigate how to find the parity of a permutation. If the number of swaps needed to transform a permutation into the identity permutation is an even number, then its parity is 0, and if this number of swaps is odd, then its parity is 1. This quantity of any permutation is constant for any given permutation, and the parity may be given by this equation, the number of swaps modulo 2. There are two main methods for getting the parity for a permutation. The first is by using the selection sort method, where we try to sort the permutation with select sort. We'll count up the number of swaps as we sort the permutation. Here is an example. We'll use selection sort to get the identity permutation. So we'll find the minimum value in the list, which should be 1, and swap it with the other element in its position. Then we'll keep moving along the list, sorting it using the select sort algorithm until we get the identity permutation, which is the permutation with all of its numbers in numerical order. Then we'll count up the number of swaps we needed, which was 5 in this case. And we'll get the parity by modulating this number with 2, which is the remainder of 5 when divided by 2. So here's the first way of getting the parity of a permutation. We'll use a method based on selection sort. We'll firstly declare the function with all of its internal variables. Then we'll load the length of the permutation into the variable n. Then we'll count the number of swaps that we made that were necessary to get back to the identity permutation. Because this is an accumulated total, we'll set it equal to 0 to start with. We'll create the outer loop to look at every element for the selection sort algorithm. We'll set the minimum value and its location in the list here to be initially equal to the first element in the remaining list that we'll sort through to find the minimum value. We can also call this the head of the list. Then we'll create the inner loop to look for the minimum value in the rest of the list. If there's an element that's smaller than the one we've already found, then we'll load its location into the location variable for the location of the minimum value, called min_i. And we'll also load in the value of this element to be the minimum value, and if these two values are different, then they'll be swapped with the head of the remaining list. After we've completed this loop, then we'll swap these two elements if they are at different locations. We'll place the new minimum value at the head of this list. And because this swap represents a permutation swap, then we can increment the number of swaps that we've found by 1 each time we make a swap. So the number of swaps will be stored in the variable called swaps, and the parity of this permutation will be 1 if the number of swaps is odd, and 0 if the number of swaps is even. This can best be represented by this modulus equation. And finally, we can return this variable containing the parity of this permutation. Now, here's another method for finding the parity of a permutation. We'll use cycle notation to find it. We'll look at this example. We'll rewrite it in cyclic notation. We could use full cyclic notation and include all the cycles of 1, but these can be ignored. So the number of swaps will be the sum of all the length of each cycle minus 1. The 1 cycles have a value of 0 and can be completely ignored. The first cycle has a length of 4, so 4 minus 1 is equal to 3 will be added to the number of swaps for this cycle. Notice that the number of swaps is equal to the minimum number of swaps required. Then the parity will be calculated by getting the number of swaps modulo 2. And here is this quite completely different method to find the parity of a permutation written in computer code. It uses the concept of cycle notation to find a permutation. Every time we have a cycle of n elements in the permutation, then we add n-1 to the number of swaps. This could give us the amount of swaps as well, and a list of all these swaps. And so we'll get the length of the permutation here, and set the initial amount of swaps to be 0, because they'll be totals during the cycle of this function. We'll set markers for all of these elements because every time we find a cycle, we'll want to ignore all of the elements that we found in this cycle. We use this technique when we convert the permutation into cycle notation. This is the loop that will cycle through every element in the permutation. We'll set this index variable to be equal to the next element in the cycle as we traverse a cycle. It is initially set to the ith element in this list, and this index variable is equal to the number of elements in each cycle. And we'll enter the cycle with this loop, but if the element is already part of another cycle, then we'll ignore it and leave the loop. We'll unmark all of the elements found in this cycle here, so that they'll get ignored in future. We'll set this indexing variable to be the next element in the cycle, and then we'll increment the number of elements found in this cycle. J should be equal to the number of elements found in the cycle after this loop is finished. It automatically finishes because the element at the start of the cycle has been unmarked. So then we'll calculate what to add to the number of swaps here. If there were j elements in the cycle, then we'll add j minus 1 elements to the number of swaps. And if this element has been ignored, then its value will now be minus 1, and so we'll have to set it equal to 0. And so we'll add this number to the number of swaps. The parity will be equal to the swaps modulo 2, and so we'll return this value as the parity of this permutation. And here's the very simple identity permutation, where every value in the list is equal to its indexing value. I'd rather just rewrite this function in the code when I need it, because it is short and faster to do it this way. And here's a function to create a random permutation. We'll firstly create an identity permutation, and then we'll jumble it using a jumble function. We have to test these functions, and we'll do this by creating functions that can make permutations that have a certain parity. Then we can compare the parity functions to see if they're equal to the value we used to create them. This function creates a permutation with one random swap in it. We'll start off with an identity permutation. We'll find the first location to swap using this random function. Then we'll find the second location to swap. It must be different to the first. We'll do it this way. We'll swap the number we've just found so it's at the end of the list. Then we'll find the next number in the list without this number that's already been found. We'll firstly find a random number in a shorter list of numbers, and then we'll find it in the list without this number. So these two random numbers are guaranteed to be different. There are other ways of doing it, but this guarantees that it can be found the first time without being in a loop to look for it again. We'll then have to make the identity permutation again. I could just swap the second random number with the last number, but it's cleaner and easier to read it if I just make the identity permutation again. And so finally we'll perform the swap on this permutation. Now to create a function that can perform a finite amount of swaps on a permutation, we'll firstly declare the function. The number of swaps performed is m. We'll firstly make the identity permutation and then apply swaps to it afterwards. Then we'll create another list called swaps, containing numbers that point to various swaps in an array containing swaps. We'll jumble this list of swaps using this classic jumble code. Then we'll apply m swaps to the permutation. We'll get two locations to swap from a list of possible swaps. We'll calculate this array in another function, which we'll describe a little bit later. Then we'll swap the two elements at these two locations, given by A and B. So here's the function that creates an array of swaps. K is the index variable to the list of swaps. We'll create a double loop to make a list of pairs of numbers, a smaller number followed by a larger number, that represent different swaps. We'll load this swap into the array so it is stored as a pair of numbers. Then we'll increment the indexing variable here, since it can't easily be calculated from the loop variables. We'll set the number of swaps found here, and here is where we'll print out the swaps. We'll create a loop to go through all of the possible swaps that we've found for this size of permutation. Then we'll load in the pair of numbers that represent this swap. And then we'll print these numbers out as an ordered pair. And then we'll finish with a carriage return at the end. And here is what the array of swaps looks like when we print it out, and when it's calculated for a permutation of length 7. Now to write up the main testing function. I've used a number of them, and this is the second one I've used. We'll make a main loop to test for permutations varying in length from 5 to 30 here. We'll have to make a new array of single swaps for each length of permutation. We'll do about 1,000 checks for each length of permutations. This goes surprisingly fast. Then we'll create a permutation with R swaps, where R can vary from 1 to 6. We'll then get the parity using the selection sort method. We could also use the parity function using the cyclic method. I've commented it out, but could easily reinsert it and comment the other parity function out. Then we can compare the parity to the number of swaps we use to create the permutation, and then if they're different, we'll print out an error message. This is the function I did in the first video on permutations. I noticed that there was a slight error and the cycle was in the opposite direction to what it should be. This could be easily remedied by inverting the permutation. I've done this by adding these 2 lines of code to the bottom. So I hope that you have found this video helpful and interesting. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. And thanks a lot for watching.